Okay, welcome to the discussion of assignment 2. This is take, I guess, 20, 13 or 14. So let's start discussing assignment 2 for your course DSAI 101. So let's start with, before I start discussing your actual question of assignment 2, let's revisit some of your basic concept, and these are the some prerequisites you need to know. That what is vector space, I hope you know already. Subspace, linear combination and spans, linear independence, and basis of vector space. I will just quickly go over all this and then start with your actual problem. So these are you know all this definition, and I will give you just an example and basic definition for vector space. So vector space over field in this video or in this lecture, of all the if I am not saying field, mentioning field, then field is a set of real number coming from R, real number set of real number. Okay, so if for any vector space over a field F, I hope you know field, what is field. So if vector space for addition, if it is a Abelian group, that means closure under addition, associative and additive property, inverse and commutative. And for second is for the multiplication, scalar multiplication, this is coming from R. Then if it satisfies all these properties, and I hope you know all these things, then it is a vector space. This Rn, you know, Rn is your vector space. This matrix of m cross n, and this polynomial of degree n with real coefficient. So these three we will be using in this tutorial time to time. And this transformation, when this will come, I will let you know what is this. Now you of course, then subspace, when if vector space is in this, if satisfies these properties, scalar multiplication of a vector and additive properties, then your vector space is a subspace as well for this one. Of course, so subspace is also a vector space, keep in mind. So that means for to show your subspace, that means you have to show these two properties, addition and scalar multiplication, and this is very important, contains 0 to show this subspace. Then linear combination, if you have given vector v1 to vk from this is a vector space, any vector space v, and all these are coming from your field, then this alpha 1 v1 plus alpha 2 v2 and so on, alpha k vk is a linear combination. Okay, what about span? Span means this span, this can be written as a span of v1 to vk, and this is nothing but this one. When someone is saying that a span of v1 v2 and so on vk, that means say alpha 1 v1 plus alpha 2 v2, any vector can be written in that vector and so on, vk, alpha k vk. Okay, any vector in a vector space v can be written as a span of your vector v1 to vk, and this is also a subspace, keep in mind. Of course, almost, let's say there is two vector, okay, u and v in a vector space, and these two are element of vector space. So what will be a span of this v? One can be written, v can be written as alpha 1 v1 plus and so on vk. Okay, u can be written as beta 1 v1 plus and so on beta k plus beta k vk. Okay, so u and vk are a span of this b1 b2 and so on, where alpha and beta coming from your field. Moving forward, so this is an example for that. Let's say v1, v2 and v3 are given like this. Then you need to show this to vector 2 3 3 is a span of this one. How can you show that? So okay, if you want to really show that, then you can take it like you can write alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. What will be alpha? And this will be as your v, where v is 2 3 3. So alpha 1 and this will be 1 0 0. This is your v1 plus alpha 2 0 1 1 plus alpha 3 and v3 is 1 1 0, and which is equivalent to your v, that means 2 3 3. Now if you, when you solve this, alpha 1 plus alpha 3 will be 2, alpha 2 plus alpha 3 will be 3, and alpha 1 plus alpha 2 equal to 3. When you solve this, you will get alpha 1 is equal to 1, alpha 2 is equal to 2, and alpha 3 is equal to again 1. Okay, that means your given vector is a span of this linear combination of given vector v1 v2 v3. Okay, hence the vector is linear combination of v1 v2 3. Just solve this equation, you will get alpha 1 alpha 2 alpha 3. Then linear dependence and independence. I hope you know all this concept. I am just revisiting this. So when this linear combination is equal to 0 vector, which implies all these coefficient coming from field are 0, then this will call linearly independent. Otherwise it is 0 if not equal to alpha r for this alpha, every alpha I is equal to 0 and I goes to 1 to k. Okay, so take an example of this independent in R2 space. So R2 is nothing, your this plane xy. Okay, R2 space is this one. So the basis is 1 0 and 0 1. These are standard basis. Let's say e1 e2. Then any vector a b can be written as a first standard basis plus b second standard basis equal to 0. Or then you can see that to satisfy this equation, both a and b has to be 0. That means these two are linearly independent. What about this? There is 3 vector in this one 1 0 0 1 and 2 3. Do we really need this to span this R2 space? Can you see this? This is a linear combination of other two vectors. Let's say v1 v2 and this is v3. Can you say that v1 v3 is a linear combination of these two? Just solve this. How can you solve this? Just as I have given you in the previous example, that v3, that means 2 3 can be written as alpha, that means 2 1 0, and this is your v1, and 3 0 1. This is your v3. So this is actually linear combination of other two. That means this vector is dependent on other. So this is not linearly independent vector. Now basis and dimension. If once you know linear independent and span of vector space B, then you can also know the basis and dimension. So basis is has to satisfy these two properties, that all the vector are linearly independent in a vector space B, and it span all complete vector space. Okay, and that for dimension, the number of linearly independent bases are the dimension of that vector space. Okay, let's see through an example. For standard basis in R3, this is your, let's say this is E1, E2 and E3. This is in R3. So these three vector will be standard basis because these are linearly independent. How can you show that? just use the previous concept and you can show that these are linearly independent, and of course you know this. And non-standard basis in R3, you can write like this one. How can you show this? These are non linearly independent. One way is to the previous one, the conventional way, as I have already discussed how to uh, mm, show that any vector are linearly independent or dependent. One is just find this determinant of this one, or from row echelon form you can say that you can find number of independent, and by forming a matrix. See, you can form a matrix 1 0 0 0 1 0 1 1 0. If matrix if this determinant is non-zero, then this is a linearly independent. And which if somewhere it is given that how many are linearly independent or dependent, from there you can use row echelon form to show that you know from the basic linear algebra. Okay, now subspace comes to the sub example of subspace. You know the subspace, and this is one of the example, this matrix, and this matrix can be written as a standard basis from basis of this matrix, not standard basis, basis of this matrix. These two will be the basis of given subspace. How can you find that? Just solve this again using the previous example. For the vector, you can simply similarly do for the matrix space. So these two are the basis of. Now these two are linearly independent. How can you show that? Again you can form a matrix for this 1 0 0 1 and 0 1 minus 1 1, and you can clearly say that there are two independent column. And so number of independent bases is your dimension of that vector space. So this vector space has dimension 2 because there is two linearly independent bases in that. Okay, moving forward, finding basis from a spanning set. Okay, if you have given a spanning set, like let's say for this example, if a vector space is coming from matrix M2, this means this will 2 cross 2, dimension will be 6 for this one. No, sorry, 6, not 6, 4. So there are these three matrices are given which span this vector space. Are these three linearly independent or dependent? So for that you have to check. How can you check that? Just write in a vector matrix like this: 1 2 3 4 1 0 0 5 1 4 6 3. Okay, now this is your 4 cross 3 matrix. Now from here you can use the row echelon form and find the number of independent and dependent column. Number of independent column. Once you solve this, I'm not going to solve it. When you solve this, you will get that this is again depend on other two matrices. So only two matrix is linearly independent from each other, hence the dimension of W is 2. Now coordinate. See, all these concepts will be used now from all this what I will discuss, which will be used in solving your assignment 2. So coordinate. So if we given vector space V, let's say vector space given is V and basis for that is given B, which have a set of B1, B2 and Bn, then it uniquely it can be written as a linear combination of the basis of vector space B, which is V1 to Vn. Now how can you write this coordinate with respect to the basis, given basis? So vector V can be written as alpha 1, alpha 2 and so on alpha n. This alpha n are the coefficient of the vector V1, coefficient of vector Vn, so on and so forth. Okay, so this is a coordinate of vector related to your given vector B. You know this. I will show this when example when we study linear transformation and how to find a transformation matrix. From there you will get to know more about it. Let's say an example of for vector space in R3. So these, let's say, standard bases are E1, E2, E3, and which are nothing but 1, 0, 0. This is your E1, 0, 1, 0. I have already discussed this as well, and E3 is 0, 0, 1. So now this vector 1, 2, 3, how can you represent as a linear combination? So this will be 1, 2, 3. Of course, multiplication with your vector space basis E1, E2, E and E3. So now this coordinate vector of V with respect to your basis E can be written as 1, 2, 3. Let's see an example of a matrix of 2 cross 2. Net standard basis for matrix of 2 cross 2 is 1, 0, 0, 0. Then 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So this is the standard basis for matrix 2 cross 2. Now how can you find the coordinate for this one? Now you have to write the linear combination of with respect to your basis. So alpha 1 E1 1 plus alpha 2 E1 2 plus alpha 3 E2 1 plus alpha 2 2 alpha 3 no 4 alpha 4 E2 2, and this will be your A. So alpha equal to 1 0 0 0 plus alpha 2 0 1 0 0 plus alpha 3 0 0 1 0 plus alpha 4 0 0 0 1 equal to 1 2 3 4. And now if you add this all this matrix, and first component will be equal to 1 after adding this will be alpha, just add it, alpha 0 alpha 1 alpha 2 alpha 3 and alpha 4 will be equal to 1 2 3 4. Now compare each element of the vector and you will get this one. So then you can write alpha 1, this is your alpha 2 and this is your alpha 3 and this is your alpha 4. Just solve this equation and you will get alpha. Of course this is a simple comparison now, and you have to do it for such example every time. Now we have already seen this vector space, subspace, span of all the linear combination, linearly independent, dependent. Okay, then how vector span this vector space, then coordinate coefficient. Now let's do this linear transformation. So for linear transformation, any map from T V to W is a linear if this satisfies these two properties, which is additivity and homogeneity. So let's understand this with an example. Let me give you an example right here, and then we will see other example as well. Let's say T is given from V to W, and let's say it is in Rn and this is in Rm. Okay, then the transformation of vector V is given as A V. Okay, and the matrix is M of M cross N, and V, your vector is V, is coming from vector space V. Now you need to show this. Let's say it is 1. You have to show this whether this is a linear or not. So first property, let's deal with this first property. So how can you prove that first property is this additivity is satisfied or not? So let u and v are element of your vector space V, then t u plus v equal to what you can write from the definition 1, a u plus v. Then this can be written as a u plus a v. And what is this? This is your t u and this is your t v. Hence t u plus v can be written as individual t u plus t v. Hence the first property is satisfied. What about second properties? Let's some alpha is coming from your field. Of course, I have already said that by default field is R for all this while I am solving any problem in this assignment or if I am giving any example. So now T alpha, let's say U equal to, use the definition 1 again. So A alpha U, and this alpha is a scalar, so it can come outside a u. What is this? This is from your definition T u. Hence the second property is satisfied. That means your given transformation is a linear. Okay, let's see another example, a simple one, so that you can understand as well. So let's say this transformation is given from R to R, R2 to R. So let's say V is given is from R2 and which is given as XY. Okay, so this TV is your XY and this transformation is given as this 2x y minus x. For additivity, let's say U is your x1 y1 and V is your x2 y2. So this is your U plus V, and then now this can be written as T individual sum of this vector x1 plus x2 and y plus y2. This is nothing but your LHS. Now after transformation, what you can write, first element will be twice of that, this will be twice of this one, so this is twice of x1 plus x2, and this is the second term will be the subtraction from second term to the first term, so this y1 plus y2 minus x1 plus x2, this is written like this one. Now when you explicitly write this one, you can write like this, and this is nothing but your transformation for first vector x1 y1, and then this is the transformation from the definition itself. Okay, now similarly you can show the homogeneity property, and hence the transformation is linear. Just quickly go over it. Now let's say this is your transformation T from R2 to R2 for the second example. When a vector, let's say this is a vector V, and we transform as this one x square y. So this is not linear. How? Just you can give an counter example. No need to solve that, or you can even show the above step and show that this is linear or not. Here I am solving for given an example. If a vector, let's say this is your V and this is U, so Tu plus Tv. So first transformation for first vector, this transformation from U is this, and then adding these two you will get as 9 0. Now this should be equal to this one individual sum, but which is not the case. Are these two equal? No. That means this is not linear, because every time first you need to solve u plus v equal to Tu plus Tv. Tu plus Tv. So this is your this one, Tv is your this one, and Tu plus Tv is this one. So you need to show that this individual sum of first one and second one should be equal to in the sum of u plus v transformation. Okay, I hope you understand this one. Now moving forward, let me give you an example for what I earlier gave. I gave you t is equal to r n to Rm. Okay, so let's say, and your transformation was TV is equal to AV in the very first example, where A was of m cross n matrix. Let's say this transformation is R 2 to R2. Okay, and then transformation, let's say matrix is given 1 0 or 1 2 0 minus 1. Okay, this will be your 2 cross 2 matrix. Now you need to show that this transformation T, let's say V, which is let's say XY, because this V is in R2. Okay, R2 means the vector size will be 2 cross 1, let's say XY. So this is 2 cross 1. This is your element of R2 XY. This is your XY plane. Okay, two-dimensional plane. Now this can be written 1 2 0 minus 1. This is your A and X Y. Now you need to show this transformation is linear or not. Of course I have already proved for m cross n. Now you need to show this. So this will be x plus 2y and minus y. This is 2 cross 1. This is in R2. So R2 to R2. I given R2. I get the output in R2. So what we have to show this first property T u plus V, let me write it explicitly, u plus V equal to T u plus TV. Okay, so let's solve this first LHS. T of, let's say x y, this is your u plus V. V is let's say wz. Okay, so let's say wz. What can be written this as? This will be x plus w and y plus z. Okay, now apply this 1 2 0 minus 1 and this vector x plus w and y plus z. Correct? Now apply this. This will be your x plus w plus 2 of y plus z, and second term will be your minus y plus z. Okay, so this is your LHS. Now what about RHS? RHS, I have written this wrongly here. This will be your TU plus TV. So what will be TV? TV will be your XY and plus second term will be TWZ, because V is this. Now what you can do, 1 2 0 minus 1 XY plus 1 2 0 minus 1 WZ. And what this can be written as x plus 2y and this is minus y plus w plus 2z minus z. If you write this will be your x plus 2y plus w plus 2z, and this will be minus y minus z, and this is nothing but your the above one, LHS. Hence the first property is satisfied. Yes. What about second properties? Let's say alpha is coming from your field, then T of alpha V is nothing but your XY. It can be written as 1 2 0 minus 1 and then alpha x alpha y. How can you write this? So this will be alpha, this will be your alpha x plus 2 alpha y minus alpha y. Okay, if you take the common outside alpha, so this will be alpha x plus 2y and minus y, which is nothing but alpha. This is your t v or t xy from the definition. Hence the second property is also satisfied. So each and every time when you want to show this where transformation function is linear or not, then you need to show these two properties. Okay, and how you can show that, I have already shown the steps. Okay, let's move forward. Okay, what about kernel and range? So I hope you know familiar with this term. This is your nothing but null of t, and this is nothing but range of t. Sometimes this is also called as image of t. So let me explain this with you an example or with more clarity. I hope you are familiar with this definition of null of t and kernel range of t. This sometimes called as kernel of t. Okay, and when I will come back to this 1 and 2 once I explain this one. Let me give you first. Let me explain you. Then I give you the example. What is? Let the transformation function from v1 to v2. Okay. So let this is your set of v1 vector space, and this is your v2. Transformation is given as t. So what will be the kernel of t or null of t? That means we are looking for a vector in v1 vector space v1 which map to 0 in v2, so we are looking for this set of vector in v1 which map to 0 in v2. So this is your null of t or kernel of t. Okay, so definition is null of t or kernel of t is a set of vector v in v1 such that tv is equal to 0. Okay, so this is your actual definition. So what it means that we are looking for a vector in v1 which maps to all the element in 0 in vector space v2. Okay, so go to the previous slide. What is this? This is we are looking for a vector in v which map to 0. Okay, so if you see this, let's say this is v or this is w, we are looking for a vector which map to 0 in vector space w. So this is your NT. I hope this makes sense to you now. Okay, we are looking for this vector in vector space b. Now extending this thing, and let me use different color. Now what is range of t? So we are looking for vector in v2 vector space v2 which map all the element of vector in vector space of v1. So now we are looking for all this set of vector. This is your range of t, or sometime no, or some literature or some paper said image of t. So these two are same. So what it means range of t? That means we are looking for a vector set of vector in vector space v2 which map all the element of vector space v1. How can we write it mathematically? Or definition is where our see all the element will be tv in this one because v is coming from vector space v1. So we are looking for tv which is element of v2. Okay, such that there exists v vector space in v1. Does this make sense to you? Okay, let me give you the previous definition. So range of t, that means we are looking, all this element will be TV in this one, all this element. So we are looking for this vector RT, which map all the element of vector space B1. So RT is nothing but we are looking for TV which will be element of this vector space W such that there exists B in vector space B. Okay. So this is your range of T or null of T. Let me give you an example. Previous example was TV which was mapping 1 to 0 minus 1. This is your minus 1 and this B was xy. Now you need to find the what is null of T and range of T. So what will be null of T? Let's start with null of T. Null of T, we are looking for vector in R2 because this transformation was from R2 to R2. We are looking for, this is your V1, this is your V2. We are looking for vector in V1 which is R2 such that TV is equal to 0. Yes, this was the definition here. How can you find this TV? We are looking for all the vector. Now just put this definition 1 2 0 minus 1 x y equal to 0 0 0 because this will be in R2 again. Okay, so if you solve this, you will get, solve this will be x plus 2y is equal to 0 and this is minus y equal to 0. Yes, that imply if you solve this will be x is equal to 0, y is equal to 0. That means this set V will be 0 0 in R2. That means this your set is 0 0. This is your null space for this transformation. Yes, now as this is a trivial set, that means number of pieces is 0. That means dimension for null of T is equal to 0 here in this case. Okay, what about range of T? When dimension is for null is 0, that means for range of T will be the complete set for this transformation. Okay, which will be a complete R2 space. What it means, think about it, or just put the definition in this one. RT, we are looking for RT, we are looking for vector in R2, this is your V2 space, such that there exists V in vector space V1 which is your R2 such that this transformation 1 2 0 minus 1 xy equal to some, let's say TV is nothing but let's say WZ which is again R2 space. When you solve this, you will get complete R2 space. Okay, complete R2 space xy. Hence the dimension will be 2 for RT. So I hope now this makes sense to you. For null space, let's say this transformation is from V to W. Then we are looking for vector in vector space B such that which map all the element to 0. For range of T, we are looking for vector in VW which map all the element of vector space B. This is the definition. Okay, let's move forward. I have said enough for this. This is an example in R3 to R2. First, this is V, this is your W, and this is the transformation. See, this is taking vector from R3 and this giving you vector in R2. Now to solve this one, for finding the null of T, you need to show TV is equal to 0. When you solve this, or let me write it formally, for null of T, we are looking for vector in V such that T B is equal to 0. Now we are looking for vector in V such that, what is this? TV will be x plus y and xy is equal to 0 and y plus z is equal to 0. Yes or no? When you solve this, this will be dependent and you will get v1 is equal to this, and this is the basis for nullity. Solve these two, what you will get? Let me solve it for you. Xy is equal to 0, which implies x is equal to minus y first, and y is equal plus z is equal to 0, that means y is equal to minus z. This is second. So how can you write this? X, y, z. This can be written x is equal to minus y. So x is equal to minus y. Y is equal to, keep it y. And then z is equal to minus y. This is nothing but minus 1, 1, minus 1. This will be the basis for your null space. Yes, this is nothing but your this one, which spans the null space of T. And then what will be the dimension of this null space from here? This will be 1 only. What about range of T? Similarly, apply the rule, definition for range of T, and you will get. So see, let's say this. Okay, let me do it for you. For range of T, we are looking for vector in W, let's say V in W, such that TV is equal to, there exists V. Let me write, there exists, this is a notation for there exists V in capital V, such that what? TV equal to W. Yes. So what is TV? From the definition, TV is equal to x plus y and y plus z equal to, let's say W is your, let's say W1, W2. Okay. This is a vector in W, which is in R2. So this is in R2. Now when you solve this one, when you solve this, just solve this and you will get a W1, W2. Can you solve this or not? You can solve this and you will get this one as a complete R2 space in R as a range of T. Okay, let's move forward. For not full range. Okay, now this is R2, R3. I will just quickly go over it. Now for range of T, you need to have this definition, range of T, kernel of T or null of T, TV is equal to 0. That means this has to be 0 and this has to be 0. And if you see, first is depend on second. Second is depending on the first element of this vector. When you substitute is equal to 0, then you will get the basis as 1 minus 1 0 and 1 0 minus 1, and this will span your null space of T. Okay, if you don't understand, just apply the definition of nullity and range of T. If you think this is very slow, then you can speed up your video and then you can see it. For range of T, this first element is S if, and then the second will be 2S. This is nothing but your S 2S. Okay, if first element is S, and then of course now this will span your range of space of range of T. Okay, so I have already given example. Let me give you an example of polynomial. Okay, or maybe in problem, I think problem assignment problem 1B, I think is given. That will be fair enough to solve that. Let's move forward. What about rank nullity theorem? So rank nullity theorem says that if transformation is given from B to W, then, so you are familiar with this one, rank nullity theorem. This says that this means that dimension of B, okay, this is already written. Dimension of B is equal to dimension of null of T and plus the dimension of range of T, which is also known as nullity and rank. So this is your nothing but null of T, this is nothing but a range of T, and this map to this one. I hope by now this you understand this one, and this map to 0, this map to 0. Okay, now let's move forward and take an example of full rank and low rank and so on. So if a transformation from R3 to R3 is given, and this transformation is given as, let's say, 1, and you know this matrix, if you remember the 0 0 0 1 0 0 1, then it will give you the XYZ. So if you find this nullity of the, you will get 0 set and dimension will be 0 for this. What about range? Range will be complete R2 space, let's say W or V. So complete W is vector space. So hence the range will dimension of range is range will be 3. And if you add these two, which will be the dimension of B, which is 3. Hence your rank nullity theorem will also satisfy. This is your dimension of null of T, this is your dimension of range of T, and this is your dimension of B, which is R3. Yes. Next, R3 to R2, I have already solved this one. If you remember from the when I was finding range of T and null of T, and from there this was your null of T. So this is your dimension of null of T, which is 1, because there is only one vector in this. What about range of T? If you remember from there, which was complete R2 space, complete R2 space, and or we can say complete W space, and so hence the dimension is 2. So from here you can say dimension of V is equal to dimension of null of T plus dimension of range of T, and this is nothing but 3. And what was null of T, which is 1 from here, and range of T from here plus 2, that means which satisfies your rank nullity theorem. Let's take an example from R3 to R2 for the second one. If you remember this, if this is S, this is 2S, second one is 2S, then nullity has 2 dimension and a range of has dimension 1. Just go to the previous example if you are writing, and then this also satisfied your rank nullity theorem. So these are the simple steps what I have already used in this one. Okay, there is one concept of on 2 and 1 1. Let me check whether so this is coming in a upcoming slide, 1 1 and on 2. So let's first how to write. Let's understand how to write, and these are all coming in your assignment too, because all this will be used in your assignment too. So how to write the matrix of linear transformation? So let's say if a given transformation is given like from vector space V to W, and basis for this is beta, which is V1 to B1, and basis for W is given gamma, then how you can write a matrix T with respect to basis beta and gamma. So this is the definition you must be familiar with, but how to use it or what it means, let's understand this with an example. Okay, and then you will appreciate it. So let's say this is the transformation V1 to V2, let's say V1 to V2, and transformation is given T of xy is equal to 2x and x plus y, and the standard basis for this one is given for both beta and gamma. Basis for this is beta and for basis for B2 is gamma. So first step, apply the transformation for first first vector and then second vector, and for both of them write in terms of gamma. Okay, how will we doing that? Let's do this. For vector space, for the first vector of vector basis of beta, this is the transformation 1 0, and this will be applying this. First term will be of 2x, that means 2 into 1 2, and 0 will be x plus y. Second term will be, so x plus 0 will be x, that means 1. Okay, so for the second, this one 0 1, this will be your output. Now you have to write this is a column vector. So first will be the first column of the first basis corresponding to first basis, that means 2 1, and second column will be the vector from second transformation, that means 0 1. So this is your transformation T with respect to beta, basis beta and gamma, corresponding to gamma. Let's understand if this is or not a standard basis for a given transformation. Let's understand this. Same, let's now this transformation, second transformation for vector xy is x plus y and y. So first non-standard, these are non-standard basis. For this is for b1 and this is b2. So this is basis for b1 and this is basis for b2. Now we need b2 means vector space b2. So again use the same steps as the previous one. So first transformation vector b1, let's say this is b1, this is b2. I mean, let me write it, let me denote it differently so that there is no confusion. Let's say this is your vector space, this is your vector space capital V to capital W. Okay, now this is your v1, this is your v2 and basis for v. Okay, how can you write this? First vector 1 1, after transformation this will be 2 1. Now you have to write this in terms of standard base, in terms of the given basis gamma for the second vector space W. Now this 2 1, this one, and now to write this, you know this step from the previous example. Alpha a10 is given first vector from gamma and second vector is 1 1. Okay, when you solve this you will get a1 equal to 1 and b equal to 1. Hence the first column of the vector matrix will be 1 1. Okay, now do this for second as well. How can you do this for second? T10 will be 1 0. Okay, yes, x plus y will be 1, y is equal to 0, that means 1. Now this you have to write in terms of your given vector. So this can be written, let's say alpha 1 0 plus beta, alpha 1, let's say alpha 2 equal to 1 1. So how can you solve this? Alpha 1 plus beta 1 is equal to 1 and beta 2 is equal to, or this is, let's say this is beta 1 and this will be 1 and this is beta 1 equal to 1. When beta 1 is equal to, no, this is not, this is beta 1 is equal to 0. What is this? Can alpha 1 plus beta 1 and then this is beta 1, this is equal to 1 and this will be beta is equal to 0. When beta 1 is equal to 0, then alpha 1 is equal to 1, hence the your vector will be 1 0. Yes, okay, same thing is given here, 1 0, hence the second column will be 1 0, hence this is your corresponding to first column and this is your corresponding to second column, which is coming from first column is this one and second column is this one. I hope this makes sense to you. Now let's move forward 1 1 and on to. For 1 1, let's understand what is 1 1 in simple English language. Let's say a function from a to b and then you can map this into vector space. Okay, and this is B, so this is A, this is B. 1 says that every element of A is uniquely mapped to uh, B, uniquely mapped to element of B. So if this is A, B, C, let's say 1, 2, 3, so there is a unique mapping. So every element of A is uniquely mapped to B. So this function is known as 1, 1. Let's say suppose the FA is mapped to the second element of, let's say, some different element B, to be this to be 1, 1. That means A has to be equal to B, otherwise this will fail as 1, 1. For the transformation, let's say B to W, and this, let's say this is vector space B, this is W. So that means every element of this one, every element, that means from here to here to here, has to map to the each element of vector space W. This is a transformation T. To make sure that means there is no nullity. That means nothing is mapped to other element of 0. Other element in, there is no two element which map to one element in W. There is no two element in B which map to one element or multiple element in W. To make sure, you have to satisfy this condition. TV is equal to 0, which means nullity of V is equal to nullity of transformation is equal to 0. If this is 0 set, then this will be 1, 1 transformation. For onto each element of B has to be mapped in some element of A. That means this is mapped to like this. Okay, that means each element of B is mapped to some element of A. Each element of B is mapped to this is known as onto. For that means you have to show that range of T. If you see this one, or let me draw this here example. This is W, this is B, this is the transformation T. Now replicate this example here for onto. That means the range space is the complete set of W, because all this element has to be mapped to this one. This is your range space. That means RT should be the complete W. Okay, W space. Let me give you the example. Let's understand this. This is not example of injective. I hope you understand this one, because these two are mapping to some element of 0, because X after transformation, this X and 0, when you put the standard basis 0, 1, the transformation will be 0, 0 for if whether it is 3, 4, 5, any y, for any y, this will be 0. All y is mapped to 0, hence not injective. Because for multiple input there is only one output, which is not the case for 1, 1. This condition has to be satisfied, which implies U equal to B for onto. Okay, now on onto, I have already said that range space has to be complete W space for onto. And now this is not an example, because the complete R2 W space is not mapped, because this is unreachable. If this is RT for this transformation, then this is not onto. Now why you understand? Because every element of W should be mapping to the some vector of W. Element of vector space B. Okay, let's understand this with example. Some example. Bijective, both intersection of surjective onto and one is bijective or on and onto. Okay, this may not be used in your solving assignment question. Let's go. This is for just for completing the theory part. Now this is, let's say this is the part A. Not, let's say this is your assignment. I think question one question. This is the transformation given. Matrix of 2 cross 3 to 2 cross 2. First you need to prove the linearity. Of course, now you know how to prove linearity. You have to take a plus b, because this and this a and b will be element of matrix 2 cross 3. Yes, and you have to show that t a plus tv, this will be equal to t a plus tv for linearity. And then again you have to take a scalar from R2, from field R, and then you have to show this linearity. Can you find this nullity and RT now? Yes, and then verify the theorem, because I have already discussed. Let's briefly go over it. Okay, solution for briefly go, and then decide 1, 2, 1. Briefly go to 3. So first you have to show the linearity proof. You have to show this first property and then second property, where C is coming from your field R, and where A and B are coming from your because your transformation is given as from M2 cross 3R, this is your field, to M2 cross 2 from R. So this is coming from A, is coming from your first, let's say this is vector space B and this is W. So vector space B coming from vector space B. Of course, now you can easily show that using the transformation. Now this is your null of T or kernel of T and T. You need to show this T is equal to 0. And just apply this theorem. I'm just for the sake of completion I'm writing this one. You will find that this is the spanning set for null of T, and since there are 4 independent matrix, 1, 2, 3, 4 number of independent matrix for this, so the dimension of NT will be 4. Okay. Now what about range of T? Of course, use same definition of how to find the range of T, and you will get this thing 1 0 0 0 1 0, and this is 2. And from here you can also show that rank nullity theorem. What is the dimension of B, which was given you M2 cross 3 R? Dimension of this is 6. Yes. And what was the dimension of null T, which was, I guess, 4. Yeah, 4. So this is your 4, and rank of T 2, that means 6, which verify your rank nullity theorem. Okay, 1 1 1 2. Of course, there is a null should be 0, but here nullity is not 0 from the definition of 1 1. Hence this is not 1 1. What about NT? On to N2 should be complete W space, right? And W is your M2 cross 2 R. So dimension of this is 4. But here what you have found? Dimension of this is 2. Yes. Hence not equal, that means is not onto as well. Let's move forward. Problem. Okay, this is your part B. Okay. How can you solve this problem? Okay, let me give you an example for this one. Let's say transformation is given problem, let's say polynomial of 3 next to polynomial of let's say 2, and the transformation is given as, let's say, transformation of px is gives to the let's say this is a derivative of this function. This is the transformation you have given. Okay, how can you show that this is the linear transform? So again, you have to show that first property, let's say Px and Qx are belong to this your P3 polynomial. So first property, what is this? Transformation of Px plus Qx equal to derivative. So this means Px plus Qx whole derivative. Now this can individually written as P derivative and Qx derivative. This is nothing but transformation of Px plus transformation of Qx. Hence the first property is satisfied. Yes. What about second properties? Let C is coming from your real field, and then T of Cpx will be Cpx whole transformation differentiation, and then alpha Px, and this Px your transformation of Px. Hence you can shown that both the properties of linear transformation is satisfied. Similarly, can you put this in this one? I mean, can you do the steps for part B? And then similarly, null of t, I just quickly go over it. Let's say this f and g are from the given polynomial, and now you can show these two properties. If this satisfied, then this will be linear, otherwise not. I hope by now you must be able to show this. What about range and kernel of T? Just quickly go over it. Again, rank nullity theorem. Once you know this, rank of will be 3, nullity is 0. When null is 0, that means this is 1 1. And when complete range is complete R2 W space, then this is your onto function. And now you need to show that each step in exam you need to show each step so that you can have full marks for the prospective. Otherwise, for understanding purpose, I hope by you know something about it. Okay, I think this is your question 2 of the assignment to solve this thing. This is, I think this is part A, which is written in theorem. Okay, so first part you can solve in this manner. Okay, let me solve this for you one first, and then you can use the similar step, and using the previous concept you can prove that. So let me give you an sketch for this first part. So if T is 1 1, that means if and only if T maps every independent subset of vector space B. So and an independent subset of W. So let me solve it for your the forward part, and then you can do the second part. So let's assume T is injective, or this is 1 1. Okay, how can you solve that? Let's suppose a set S has vector b1, b2 and so on. Let's say bk. Okay, which is subset of your vector space B, and these two be linearly independent. These two be linearly independent. How can you show that? Use the definition for linearly independent. So first write the linear combination of all these vector b1, alpha 2, v2 and so on, alpha k, vk, and what will be this one? So this is the linear combination of all the vector in V. Let's say if this is V, then TV can be written as T of alpha 1 V1 and so on plus alpha k Vk. Yes. Now for I have supposed that to be linear independent flows from 1 1, that means this has to be 0. Yes or no? So this has to be, that means TB has to be 0, which implies U has to be this TB has to be 0, B has to be 0, which implies alpha 1 V1 plus and so on alpha k Vk has to be 0. What is this definition of? From this linearly independent of your set S in vector space V, from the linearity we can say that all the alpha, every alpha I has to be 0 for I is equal to 1 to k. That means this set is linearly independent. Which set? This S V1 to Vk is linearly independent. Similarly, the second part, this you can show by contradiction. How can you show that? The transformation T has to be every linear element subset of B has to be linearly independent subset of W. To show this T is 1 1, it should be the set of this thing T of B has to be 0 set. Yes, that means B has to be 0. That means B has to be 0, which implies the nullity of T has to be 0 set. And when this is proved, that means this is 1 1. Yes? Okay, let's move forward. Okay, this is your second problem. If T is 1 1 and S is subset of B, then you can solve this. How can you solve this? Let me give you an example, a sketch of this. If S is for first case, forward case, if S is linearly independent, then from part A, T will be, transformation of TS will be linearly independent, as I have already proved this from the first part. And TS is, let's say TS is for the second part, TS is linearly independent. That means alpha 1 V1 and so on, alpha, let's say k Vk has to be 0 for every all this Vi element of S. I have already considered that this is V1 to Vk in the first part. Yes. Now if you apply this linear transformation, how can you write that? If you apply T alpha V1 plus and so on T alpha k Vk, which has to be 0 of course from here, and then alpha k T Vk plus, from linearity you know this second part, T V2 and so on, alpha k T Vk has to be 0. Yes, and from linear independence again alpha I will be 0 from the property of linear independence, which implies this TS is linearly independent. Don't you think so? Just think over it and you will know. And this is your third part. Can you do this now? I hope you can do this. Or I think this all this I have given in your book, reference book, which I mentioned in your assignment question. Let's move forward. Oh, I think this is a video lecture. You cannot ask question, but I think you can drop on LMS. where you can drop maybe we can create a question dot for assignment 1 and assignment 2, and there you can write your question, and if all those questions are common or relevant, the respective TA can answer that. So I think this will be a best idea to answer all your queries. Now let's go to this question 7, I think, which you need to find this matrix. And what do you mean by this one? Now you understand that. For your question, the standard basis is given for beta, and the second for RM based standard basis is given gamma. So now you need to find this. This transformation matrix will be of M cross N for beta and gamma. And this is what this is mean. I have given the definition earlier as well. Now this is the simple steps you need to follow, and I have given some example there. Now let replicate that in your assignment 2 questions. So this is your first question. The transformation is given as this. Just check your assignment question. Now your objective is to compute this transformation T for basis beta with respect to gamma, where the standard basis in R3. We already know this standard basis in R3. Now I have already told you first corresponding to transformation corresponding to first basis, second basis, and third basis, and write them as a column of that in terms of the basis of gamma. The second vector space. Let's do that. This is your transformation corresponding to first basis. After applying this transformation, let's say A, transformation A, you can easily write that corresponding to second basis, corresponding to third basis. Now this first is written as the first column, 2 minus 1 1. This is the second column, 0 4 0, and this is your third column, 1 5 1, and which is of 3 cross 3 because your transformation was R3 to R3. Okay, every time once you need to do this thing. Now this is your second part, where the transformation B is given. So in your question this was missing, or you can make sense like A minus 2 plus A n minus 3 and so on. Finally it will become like A3 plus A2, then A3 2, this will be 2 plus A1, and finally A1 plus A0, but 0 is not there, so this will be up to 1 because I is coming from 1 to n. You must have a question with you by now, and this thing can be written as this is a transformation for every I. Now how can you write this matrix? Let's do this. Once you apply this standard transformation, standard basis in each transformation, you will get, let me do it for you for one. Let's say the standard basis will be 1 0 0 and so on 0. Second will be 0 1 1 0 and so on 0, and so on 0 0 0, and finally it will be 1. Okay, when you apply this first transformation, you will get first only the first element is 1, otherwise rest is 0. So first element is 1, that means only 1 will be 0, otherwise all the element will be 0. Yes, so likewise here this is 1 for all this diagonal, otherwise it is 0. Then sub anti-diagonal it will be 0, because when you put this will be 1, this will be 1, other term will be 0. Yes, when A2 will be, this is your A2 and this is your AN. For AN only this term will be 1, other term will be 0. Okay, because all these elements are 0. I hope this makes sense. For example, I have computed for n is equal to 5. I hope this will make you sense. Just look over it. Or if you have a problem, write on LMS some question if this subsection is created there. Check this also for better understanding. Of course, now you can do this one. I don't have to explain this because this is straightforward now. What about this question? Your transformation is given from matrix space to the polynomial, and this is the transformation is given. The standard basis for the matrix of 2 cross 2 is this one. I have already discussed this one. And for polynomial of degree 2, it will be 1x x square. This is the standard basis for P2. Can you find this now? You can pause this video and try to solve it yourself. The each steps is given like this one. Once you apply the first standard basis, you will get this vector will be this. Similarly for the second, third and fourth, and now stacking this into the column of the matrix, and you will get the matrix as this one. Okay, direct sum. Okay, I think one of the question is about direct sum and proving the direct sum. What time it is? Video is I think already 1 hour 21. So okay, I will give you this. Okay, let me make you understand. I mean, see, this is I will quickly go over it. So direct sum, you need to have this a basic concept of intersection. Let's say this and this one. Let's say this is your vector space V. Let me use different color. This is your vector space, let's say U, and this is your vector space W. This part is known as intersection U intersection W. Okay, so there are two concepts, sum and intersection of vector space. Okay, so this is intersection of two vector space, or if you see the diagram, this is your vector space, then U and W are the subspace of vector space W. So this is intersection of two subspace, and this is the sum of two subspace. So what it says that if direct sum of U and V is equal to vector space V, which has to be satisfies these two properties. That means if and only if sum of two vector subspace is equal to the V vector space and the intersection this has to be 0, then this is called as direct sum. Okay, and keep one more thing, this is also subspace and this is also subspace. I think I can prove one of them, on second one you can prove yourself. So that this let's say U intersection W is also subspace for vector space V. To show that, you need to show that if 0 is element of U and 0 is element of, let's say, this vector space W, then that means 0 is also element of U intersection W. Second property, let's say V1, V2 are element of U intersection W. That means V1, V2 are element of U and V1, V2 are element of W. That what it means, that means V1 plus V2 are element of U. What this means, V1 plus V2 are also element of W, which implies V1 plus V2 are also element of U intersection W. Second property. And third, we have to show the scalar multiplication. Let's say V is element of U intersection W. Let's say alpha is your coming from your field R, which implies RV is element of W, which implies RW, RV is element of W, which implies RV is element of U intersection W. So all these three has been satisfied. That means is a vector subspace in capital V vector space. Okay, that's not the objective, but we have to understand this direct. So if a vector space V has subspace U and W, then U plus W is called the direct sum. If any element U, V can be written as uniquely. How can you write uniquely? When this intersection set is 0, then this will be a direct sum. Okay, and this is the notation you know. Let's see this example of R2 space. Here V is in R2, and let's say U and W are the subspace of vector space B. Is this a direct sum? Let's say, let me give you an example. Let's say let's say U is let's say A 0, and A is coming from your field, and this is nothing but your x-axis. Let's say W is defined as 0, let's say B, where B is coming from. This, remember, every time when I'm using this is a set of B. Now can you show that this is a direct sum? No? What is the U intersection W here? This will be nothing but a 0 only, or you can write like 0 0. Yes. And what about U union W? And what about U plus W? What is the difference in these two? Let me give this as video is very long. I'll give you an example. So first, what will be U plus B? I will give you that A plus B, where A and B are element of R. Let me write it as set. Okay. So this is your R2 space, which is a direct sum of U and W. How can you represent this? Let's see an example. Same thing I have represented like this one. This will be your complete R2 space, which is a direct sum, which has a subspace U and W. U is x-axis, W is y-axis. Okay. So I think most of the problem from linear transformation, then null of T, range of T, their dimension, rank nullity theorem, 1 on to, then how to find this transformation matrix for given basis, whether it is standard and non-standard basis, then finally this direct sum. And some problem are based on your applying this multiplication of matrix that I have excluded because that is 12th standard. You can do that multiplication of two matrices. I hope this completes the assignment 2 discussion, and I will try to upload all this complete solution. Actually, I discuss all this on some this but that video was not completing everything, including, or there was some noise and everything, so I stopped recording that. Anyway, okay, best of luck. Okay.